listening to your journey so far, it feels like you've made three bold choices that have brought you to the point where you are today. So, from choosing a major in chemistry from Drexel over music, to applying machine learning in chemistry, to applying your research work to solving problems in sustainability and environmental remediation, how has your approach in making these decisions evolved from high school to postdoc?
Wow, that's a that's a big question. I mean, in high school, I wasn't really thinking about these problems too much. So it may be more relevant to think about starting from college. But I mean, in high school, I was thinking about how can I marry my love for music and my love for, understanding what's going on under the microscope per se. And so that led me to engineering. And then engineering, I was thinking about, I was actually more interested in the basic science. And so that, realizing the job opportunities that, or at least were presented to me, I realized that I wanted to be more involved in the basic science. And so doing basic science research then led me to understand how I can use a simulation to actually predict something that might happen in the real world. And so that was a very exciting moment. That was a pivotal moment because then I could, learn how to tailor a calculation to, understand some trend that might enable me to make a better material for a system. And so now that I'm, and then in my PhD, I developed that expertise so that I wouldn't have any issues with the calculation end of things. And I started realizing, some limitations in how we model catalysts. And then by the time that I've, gotten here now, I now have, the tools to perform a series of calculations ranging from the quantum mechanical or the dynamical through, a classical simulation. But also now I have a better sense as to, what types of calculations can I do to probe a system and what are the important variables that define how the property of interest changes with respect to changes in the material. And so it's, at this point, I would say that in my postdoc, I'm really building upon my understanding of the simulation and how to develop a more realistic pipeline for materials discovery. But now I'm learning more so, what are the key elements, how can we create materials design frameworks? How can we look at the periodic table and say, I think that actually this would be a great element to put in here. Or how do I look at, a system and say, this might have very interesting surfaces for this process. So over time, there's not one path. I would say that, it's really unique for every single person. But for me, it was more, I loved the microscopic world. I loved atoms, I loved molecules, surfaces and their interactions with molecules were unbelievably fascinating to me. And so it really started with just a passion for the unknown. I like to say sometimes that, people in the sciences are kind of like explorers, back in the, 15th, 16th centuries, explorers were exploring the world. But now, that world has been explored and civilized. And the rest of there are two remaining worlds to explore, space and the microscopic world. And the microscopic world is fascinating. And I got into that. But then it was realizing how you can control the microscopic world. And by just changing subtly the interactions between atoms and how they're positioned with respect to one another, you can make a change that manifests itself on the size of the visible world. And it can change devices. And it can make devices more efficient for solar energy or for the production of fuels. And building that bridge was my PhD and postdoc, and that's what got me to where I am today, where now I have a set of tools from physics that I can use, a set of tools from machine learning that I can use, a general knowledge of chemistry and physics that allows me to think of systems without having to do a simulation, getting a sense as to what should happen, and then now how to basically put all of those things together to create a really compelling argument that a material that I may have discovered is really promising.
Yeah. And what have you learned working with Professor Carter, who is well known for the discovery and design of molecules for sustainable energy?
I've learned an incredible amount from Professor Carter. I've learned how important it is to stay focused on the application. I mean, she has built her career on developing theoretical methods, from embedding theories so that you can do a very accurate simulation on a few atoms and then treat the rest of the atoms using a more efficient method, so that you can really get an accurate estimate as to different chemical reaction energies, to her development of orbital free density functional theory, which is a very neat way of doing a DFT simulation that's actually more in the spirit of the original method. So she's most of her career has been theoretical method development, but she has this real important drive that what she does in the lab also has to make an impact outside the lab, and I think that that's played out in her career in terms of she developed the Andlinger Center at Princeton, which was their energy center, and now she's a dean of research and driving the direction of the entire research of the University of UCLA. So I think the main thing I've learned from her is how to stay deeply connected to the problems that need solving. And I really enjoy, trying to figure out how can I use, my knowledge to make a very, speedy impact on, the future of the world, especially with, the way things are trending and the need to develop new sustainable energy technologies. I think that the lessons and the skills that I'm learning from her will enable me to make an impact quicker and be able to, screen materials faster, but to do so in a incredibly rigorous way. I would say that's another aspect of working for Professor Carter, is that she cares very, very deeply about the details of the simulation and making sure that, you've considered the possibility that the simulation itself is too coarse and that you may need to refine certain aspects of it. And her knowledge is incredible in this area. And so it's really made for a scenario where I've learned how to, not only, apply my knowledge better, but also to refine the calculations to a point such that, we can trust that an experimentalist may be able to come along and make the material we're interested in or observe the phenomenon that we're observing.
Yeah. And what are your role models in the field of chemistry?
Oh, wow. I would say that, well, I mean, it's easy to say Jens Norskov is a very famous researcher in the area of catalysis. And I think what makes his work so impressive is how he takes something like heterogeneous catalysis. And for those who don't know, heterogeneous catalysis is, the catalyzing of a chemical reaction at the interface between two phases. And so it could be a solid phase and a gas phase. So you have gas molecules coming to a surface, or it could be solid liquid phase. You have, molecules in a liquid and they diffuse to the surface. But anyways, he developed theories for, the interactions of species at the surface and their relationship to the interactions of other species, as well as, understanding for how do the fundamental electronic properties of a material relate to the binding and the catalysis at these heterogeneous catalyst surfaces that are just very elegant and beautiful and help you to understand on a very intuitive level what's going on from a chemistry standpoint. And he's one of the people that I admire the most, because he takes this almost like Einsteinian principle that you should always, or it's also Occam's razor, that you should seek the simplest solution to a problem. And I think that his solution, or at least his understanding of heterogeneous catalysis, is just so elegant and beautiful that you can understand it whether you're a professor at a university or an undergraduate, perhaps even a high school student, and it enriches the field. And so I try to, myself, to also model that in my research, to try to find the most simple and elegant solutions to a problem that allow not only us to solve a problem, but also for people to understand it, and for people to, for there not to be a barrier for other people to want to apply it and to add it to their, their knowledge and, their toolkit to how they solve problems. So I just think he's made incredible contributions, and I have learned from them and I use them on a daily basis.
Yeah, I think that is what it's about, just simplifying a really complex topic so that everyone can understand it. Yeah,
That's I think yeah, it's one of the most wonderful things in science beyond solving an applied problem is finding a simple model for a complicated system, and to be able to then, you know, see how that system changes under the constrained variation of just one variable or a few variables. And that's a beautiful thing, because I think that this happens a lot in physics, where, or in chemistry too, where, you know, really complicated systems, sometimes you can understand them in a very simple way. And I think that that should be the goal, always, to try to find the simplest model for a complex phenomenon.
yeah.